Now, the very last thing in section 10.6 deals with Kepler's laws. Now, there's some book calculations. I'm going to kind of skip the book calculations, and I just want to give you an idea of Kepler's laws and how they're applicable to these polar equations especially of ellipses. So Kepler's laws have to do with the orbit of planets around the sun. So when a planet is traveling around the sun, Kepler observed that each planet moves in an elliptical orbit where the sun is a focus. So a sun is a focus of this ellipse. So each planet does that. Now, later on, these laws were improved by Newton, and it turns out that these are sort of this Kepler's observations also applied to any sort of universal laws of gravity. So, any sort of objects moving around other objects. So, for instance, asteroids moving around big bodies, uh, orbiting around certain things, or moons orbiting around really big planets, or comets orbiting around the sun, and things like that. So, not just planets, but so Kepler's law says this. It also says that a ray from the sun to the planet sweeps out equal areas of the ellipse in equal times. Now, that one might be a little bit hard to understand, but equal areas of the ellipse in equal times. So, what does that mean? Well, let's think about a graph of an ellipse. So, here's what I have an ellipse. Now, I'm going to try to draw on this, but it's going to be a little bit easier to see if I draw this on a polar axis grid. So we found out how areas and polar forms look like. So what is an area? Well, when I am trying to find an area in polar form, well, last section I saw that if I was looking at from the area, if I was looking at the area, what I do is I take sections of pi, sections of this pi here, and add them up. Okay. So let's say I wanted to focus on the area where theta was between 0 and pi over 2. So this section here. So what it's saying is if I take another section of this ellipse and it has equal area to this one, then the planet will have traveled along the ellipse from this point to this point at the exact same time it took in the other section. So let me give another section. Let me draw another section, perhaps. So I'm going to try to figure out one with equal area. Maybe it's something like this. Here, equal area. Well, shoot, I don't know if that's equal area or not. I'm not drawing this very straight. I apologize for that. I think that's going to give me a bigger area. So let me erase that. Right, so sorry about that. I messed up. So basically, here's what I'm saying. Now that I've drawn this, so let's imagine that this red area is the same as this purple area. So what Kepler's law is saying is that if these two areas are the same, again, notice that they were both created by rays from the pole, in other words, rays from where the sun was at, then the planet is going to travel along the ellipse, at least the red section of the ellipse, at the exact same the exact same time it takes that planet to travel along this purple section of the ellipse. So the red section of the ellipse here is going to take the same time to travel as does the purple section of the ellipse. And so notice, because when we get further, our rays are going to get longer out. That's going to give me more area in these rectangles. The further your planet is away from the sun, the slower it's moving along the ellipse. All right. Hopefully that makes sense. And the closer it is to the sun, the quicker it's moving. So that's what Kepler's law is saying. Or at least that's the second portion of Kepler's law. Now, the last portion of Kepler's law says the square of the period is proportional to the cube of the mean distance between the planet and the sun. So the period at which the planet takes to go all the way around that ellipse is proportional to the cube of the average distance between the planet and the sun. And so if the average distance from the Earth to the sun is, let's just call it a unit of 1, because Mars is further away, it's going to take Mars a longer time to travel around. And how you can calculate that is by this average distance between the planet and the sun. So those are Kepler's laws. Again, I'm not going to do a lot of calculations, but I did want to introduce you to those. And that's why writing these polar equations is so beneficial with Kepler's laws. You can see that whenever you write a focus at the pole, well, that means your pole is acting sort of as the sun in Kepler's law, as long as we have an ellipse, obviously. So that's the idea behind Kepler's laws. And that is the end of section 10.6.